Hello, and welcome to the iSystem webinar series. Today's episode, the first in 2021, is about non-intrusive on-target software test without code instrumentation using iSystem tools. We'll learn how to increase the quality of your software by using the iSystem test tool called testIDEA. My name is Chris Schlink, and today I'll lead you through the wonderful world of on-target testing. I've had the pleasure of working for iSystem for over 16 years, helping customers utilize iSystem's powerful development and test solutions. Before we start, I'd like to go over some general information. During the webinar, everyone will be muted. If you have questions, please use the question tab in the menu bar. Below the question tab is the handout tab, which allows you to download the slides from today's presentation. Today's episode will also be recorded and published on the iSystem YouTube channel, so be sure to check that out to view the many other webinars we've published for our customers. At the end of this webinar, a few of your questions will be picked and answered during the Q&A. All other questions will be answered by email afterwards. In today's webinar, I'll show you how to prepare on-target tests without any code instrumentation. You can test your production code even with optimizations enabled. I'll show you how to inject faults during a unit test. We'll take a look at how to prepare stubs for nested calls. I'll show you how to measure different types of coverage, like statement, branch, and call coverage at the object level. That allows you to run coverage on compiler, linker, or other generated code that's not directly traceable to source code statements. We'll take a look at the test reporting features. And finally, we'll generate a JUnit compliant Python script for continuous integration testing. I'd like to first take a look at functional safety standards, their origin and how they've evolved over time as technology is embedded deeper and deeper into our daily lives. After a short introduction to testIDEA, I'll switch to a live demonstration where I'll touch on unit tests, stubs, fault injection, coverage measurement, preparing reports, and generating JUnit compliant Python script for continuous integration. We'll finish the webinar with a short Q&A session. The origin of functional safety standards is the avionics industry. DO-178B and now DO-178C generally provide the most specific guidance in terms of test activities required for functional safety. In industrial control, IEC 61508 took many of the same principles from the avionics industry and generalized them. Once generalized, standards for other industries have been adopted to address the specific needs of those industries and made sure that they were accounted for in those specific standards. All other industries that use software and hardware to control safety critical systems require certain levels of testing to ensure functional safety requirements are met. Lifts, elevators, and escalators need to be tested. The industrial market has its fair share of functional safety standards. Of course, medical devices and their software must be tested. Household appliances like washers and dryers, or refrigerators or stoves, must meet their functional safety standards. The energy sector controls a number of safety-critical systems and must also do its part in keeping people, communities, and the planet safe. One of the most recent standards to be defined by the International Organization for Standards is ISO 26262, titled Road Vehicles Functional Safety. It's an international standard published in 2011 and revised in 2018. The automotive and transportation industries in general are going through a sort of renaissance at the moment, driven by advances in hardware and software technologies. With its roots stemming from DO-178B, functional safety adopted a generalized standard in the industrial IEC 61508, which is now known as the Basic Functional Safety Standard, applicable to all kinds of industry. Buildings, industrial, medical, household, energy, and transportation. Testing is an integral part to keep all of us safe on the drive home or the next flight that we might take. This year at the CES, GM announced an autonomous VTOL, which stands for vertical takeoff and landing, a Cadillac. It's not really a flying car, so no road testing required. I have yet to see anything like the Eagle 5 from the cult classic Spaceballs, though. But maybe once Elon sets up his Mars base, we'll hear about the Tesla flying RV. Whether you're testing an avionics controller from a spacecraft, or an automotive controller from an autonomous vehicle, iSystem can help you develop and test to compliance of any functional safety standard. Looking closer at the avionics and automotive development, they both use safety integrity levels to manage risk of catastrophic failure. The higher the integrity level, the more stringent the required testing becomes. Each controller is assigned a safety integrity level based on the inherent risk of catastrophic failure that could lead to loss of life, significant property damage, or damage to the environment. The code coverage requirements are directly related to the safety integrity level of the system under test. Let's take a look at typical ECUs found inside an automotive vehicle. Each system is made up of different controllers or ECUs, which fall under different safety integrity levels. ASIL-D are the most safety critical controllers and require the most testing. ASIL-A are the least safety critical and require the least testing. When you look at the different test tools on the market, you'll notice they all tend to focus on instrumenting or modifying the code base in order to implement test cases. Then, the modified code, sometimes recompiled for different architecture, can be executed natively on a host PC or in a simulated environment, or on the target system, if the modified code still fits in the intended memory. Then, tests are executed, and the results are read back to the tool. The main problem we see with traditional testing is having to instrument your code. What if there was a way to run automated unit system and integration tests directly on your code base from a continuous integrated environment? That's exactly what testIDEA does. testIDEA is a test framework that can configure your target development environment into a full hardware-in-the-loop test environment. The target is configured for whatever state you are testing. Power on startup tests or failure modes. Everything you expect your controller to handle can be tested without instrumenting your code. Compiler optimizations can be enabled. All tests are executed on the target system. The test setup consists of an iSystem debugger, target ECU, and host PC. Here we have an IC 5700. The 5700 is connected over Ethernet or USB to the PC. The target MCU is connected over a debug connection like JTAG, DAP, LPD, or SWD. And additionally, if the device supports a trace port, you can record program trace, data trace, and other trace messages. These features ultimately depend on the target MCU, so check with us if you aren't sure if your device supports trace. We'll check all the options you have. Sometimes you can use a larger pin device from the same family in place of the production device to get trace, just for development and test purposes. iSystem also provides add-on modules for analog and digital I/O, as well as CAN and LIN. These can be connected to the IC 5700 system to create a hardware-in-the-loop environment or automated test environment. Add-on modules can be used for recording analog and digital signals and for recording traffic on CAN and LIN buses. Tests can be executed in testIDEA or via Python scripting. You can create a black box or white box or hybrid testing environment. In essence, testing your hardware, compiler toolset, and code base by utilizing the target environment as the test environment. This setup is easily scaled up to your needs. We get requests for test stands with hundreds of systems installed. All test systems can be controlled by a single PC or can be distributed as needed. Ask your sales rep about our new continuous integration license, and let's start discussing your testing needs. One requirement of testIDEA is that stack memory must be initialized. You could also initialize MCU peripherals, clocks, I/O ports, external memories. The code under test must be operational on the target system in order to be tested. The most basic initialization would be to download the code under test to the internal memory and run until main, thereby initializing the stack. In order to perform a unit test, testIDEA prepares a call stack frame for the function under test, and function attributes are pushed onto the stack. testIDEA then starts executing the function under test with a call from the stack, and the embedded software starts running until the function returns. When the test completes, testIDEA evaluates return values and other test values against expected results. Execution returns to main, and the next test starts. testIDEA does not restore values of global value variables or special function registers automatically. It is the test engineer's responsibility to take care of the initialization of these values before each test. Unlike unit testing, system tests don't manipulate the stack. The system test starts at a certain user-defined entry point. The system test runs the code under test until the endpoint is reached. testIDEA values are then checked against expected results, and reports can now be generated. Now I'll move into the live demonstration. Okay, so here we are in winIDEA. winIDEA is our integrated development environment. winIDEA actually stands for Windows Integrated Development Environment Advanced. It's a lot like Visual Studio. It's got right-click context-sensitive menus in all of the different windows. There's drag and drop functionality, so you could look at, things from either functions or memory. Variables in just by dragging them into the watch window. There we go. You've got other windows, so your watch window, you can add watches. The locals will automatically populate. You do have debug functionality. You can, step and everything inside the disassembly window. winIDEA works off the concept of an active window. So if the disassembly window is the active window, you can tell by the title bar if it's solid. Then all of your debug commands, step, will be on a disassembly level. If you are clicked in the source window and start stepping, then you'll be stepping at a source level. Okay, so debugging is pretty straightforward. So let's get into the testIDEA. So in order to launch testIDEA, it's under test, launch testIDEA. And then it'll prompt me to open up my YAML file. So the test specification is actually done in YAML. It stands for yet another markup language. So it's just a text-based markup language file that keeps all of the test parameters and all of the environmental kind of settings and everything. So you could open it up in a text editor and take a look at it if you wanted to. You could even copy and paste sections of it if you wanted to kind of duplicate or even create your own test specification through some kind of code generation. You could totally do that. Okay, so the specification I'm using is actually under here. Okay, there's my YAML file. Okay, so I've got a few test cases that I have already set up here. It's basically all, so I'm in unit test mode, so this is all unit tests. So each test here, this is where we have all of the tests listed, and you can, group tests, create subgroups or groups, or, create new tests or derive tests from existing tests. So you have some options, just like winIDEA, you have some special options in each window. So for each test, you have these different components that you can set up. So the meta is where you put ID information, any kind of description or requirements. So this is where you'd put all of the different requirements for this test if you're doing requirements-based testing. Next, you have the function. So this is where we can refresh the symbol information from winIDEA, and now we can actually select a function from a drop-down list, or if you wanted to actually like start typing a function, you can find the function that way. This test is for this function. So it does give you a prototype of the function. So we've got a function that takes a structure, parameter, and returns a short. So here's where we actually pass the parameter that we want to test with. So this could be a raw value or some kind of structure, either that exists in memory already, or if you can create it dynamically. So like just for testing purposes. So here we'll go to the variables section. So I'm actually creating a new variable, just a local test variable. The original variable is named S1. So if I were to have used the name S1, then it would have actually used the variable that's defined in the actual source code. You can do that. That's perfectly fine. But for testing purposes, you can also just give it a different name, and then that variable is actually created for you, and you can initialize it, and then you don't have to mess with any of the local or the global variables. So you can do it either way. So for this test, I'm creating a local variable, and we're going to initialize it here. Persistent variables. So by default, local variables are actually like dynamic local variables that you're creating just for the tests are destroyed after the test. So if you need to create a variable that exists beyond this test for multiple tests, you can use a persistent variable. Or you could also just use the actual variable from the function, S1. If we declared S1, then S1 already exists in memory. This function would manipulate it in some way, but it would leave it in memory. So globals and register values are left unchanged after the test completes. So whatever the test did to modify a global variable or a register, those values remain there. So it's up to the next test if those values need to be reinitialized or changed in some way, then the next test has to take care of that. Okay, so for this test, it's a very simple test. We're just going to be initializing the structure and passing it to the function, and then we're going to be checking the return value, and that's it. So the other features that we have here is we can set up preconditions. So preconditions are checks that would be made before the test actually executes. So we had a lot of customers that were complaining of their tests failing, and it turned out that the state of the target before they executed their test wasn't what they expected it to be. So we set up this preconditions feature. So now you can set up conditions that are checked before your test actually executes to make sure that things are the way you expect them to be for the test to execute properly. The next feature we have here are stubs. So stubs are a feature that are very common in testing, where basically for unit testing, if you want to be testing just a single unit, you do not want a nested call to pass some undeterministic data to your function. So you can use a stub that basically avoids the call to the nested function, and then provides a return value automatically. So we can look at one of these tests here that I have set up that uses stubs. So here's one. So this function here actually has, just for testing purposes or sample purposes, we have a function called function stub that's going to be stubbed out, and we're providing a unique return value here, 10 on the first pass and 11 on the second pass. We have the return name that we're using. We can also pass parameters directly here if we want to. If we want to actually like run the stub. Is active is yes, the stub is active. So no would mean that the code would execute. You can also set up a custom active where you can actually provide parameters here. You can also set up a script function, a Python function, to do any type of setup that you want for the function. You can also set up a constraint on the number of hits. So if you expect the hits to be less than or greater than a certain value, so the number of hits is the number of times this stub will be touched, during the test, how many times it would be executed, and we'll just be returning a value automatically. We also have user stubs. So user stub is a unique feature that provides the ability to either skip the stub, so you can do that with a normal stub too, but with this one you can actually replace the function with another function. It has to be of the same prototype, so we have the existing function and its prototype, and here's the replacement function with the same prototype. So just for testing purposes, you can set up a user stub that maybe substitutes some special code to exercise some kind of special test procedure. Next we have test points. So test points are the fault injection feature. So test points allow you to basically stop the test at any given point and modify something in order to see if the code can handle like a fault or some kind of error that you've injected, to see if the code can handle it. So again, we can choose what function we actually want the test point or the fault, or the injection, I should say. It doesn't have to be a fault. It's just some kind of a test point where we're going to stop the system to do something. So we've got two different test points set up to exemplify the different ways to set up the test points. So depending on who's doing the testing, sometimes test engineers don't have access to actually modify the source code. So in this case, we can set up a test point just on the unique line of code. So in this case, we're going to be searching the function, the module where this function is in, and we're going to be starting from line 0. We're going to be searching in code only, plain text, and we're going to look for the pattern, this return ret pattern. And so that's one way you can set up a test point to try to find a unique line of code to set the test point at. The more convenient and sort of recommended, if you have access to actually modify the source codes, you can set up a comment, and then you can place the comment wherever you want on any line of code where you actually want the test point to be set at. So in this case, again, we're going to be searching from line 0, but in the comments only this time, and we're going to be searching for a special comment, testIDEA, test func. So those are the two different ways to set up a test point. And once you have the test point set up, then you determine what exactly you want to do. So here we're going to be replacing the return with return plus 11 on the first pass, return plus 22 on the second pass, and return plus 33 on the third pass. We're also going to be logging off the pointer to A, the A pointer, and return, both before and after we do the logging or the assignment. Okay, so that's so a very simple action that we've set up for the test point. You can do a much more sophisticated action, like create some kind of corruption of the ECC or some other more sophisticated type of failure using this script function here. So you can basically execute a script when you hit this test point, and the script can really do anything you can manually do in the debugger. So the debugger is running behind this as well. I forgot to mention. We launched testIDEA from winIDEA. So winIDEA is always running in the background. So anything you can do in winIDEA, you have access to within testIDEA as well. So we could write a script function that, reprograms some memory, or sets up some type of fault state that we want to test. Excuse me. Okay, so that's the fault injection feature. Next, we have the coverage measurement. So coverage is actually done in two ways. The recommended way is if you have access to a trace interface. So the trace allows you to record program and data execution while the system's running. It's completely unintrusive. It usually requires a special device, either a special pin package or a special emulation device. So for example, in this case, I've got an Infineon Tricore TC277TF device, which is their emulation device. So it's a special device that you can get from Infineon that has a little bit of extra memory for this trace feature. And that allows you to basically record some program execution or data access while the system's running. And then you can use that feature functionality inside the test tool as well. So you can set up constraints. So for example, we could set up the coverage. The coverage is basically what lines of code were executed, what branches were taken, that type of information. So here we would actually specify the function that we wanted to run coverage on inside the test code that's inside this test case. So for example, we have, here's a test case that has two functions that we're going to actually run coverage on. So the first is the whole function that's being tested, and we expect 100% object code. We could also put 100% source line code, I believe. That should also pass the test. I don't believe there's any conditions in this test, in this function that executes, so we don't have any information to input here. The other function that we have listed here is func stubs. So this one's specifically here for testing purposes or example purposes to be stubbed out. And so we are going to specify 0 bytes of coverage for the function stub, because again, that's the one that's actually going to be stubbed out, and we're going to be providing a return value of 10 for that nested call automatically without executing any code. So we expect 0 coverage for the execution of this stub. Let's go ahead and run this test case and see what we get. Okay, so in this case, probably the code was still running, so I'll go ahead and cancel, and we'll just take a look to see where we are. Okay, so we're stopped. Okay, so I stepped a few times. So let's go ahead and just, we'll go ahead and init the target from the testIDEA tool. That'll be a way to get control. So here we have an init target option. And so what I just did with the init target, that's actually something that we want to take a look at in the beginning. This is something that you want to set up prior to running any tests. So the initialization that I have set up is just to perform a download and run until main. So that ensures that the stack gets set up. That's really the only requirement for the test tool to be able to run these tests on the target system without any instrumentation. So the other types of initializations that you could set up are, so if you have a multi-core system, you could connect to a certain core. Maybe you only want to run code on a specific core of your multi-core device. If maybe you need to set up a kind of a longer sequence of things where you're going to maybe download, run until a certain function, maybe then wait until you're stopped because you have a breakpoint there, and then you're going to reset and maybe call a certain function or a script function to do some special initialization. You can do all this in this area, but you have to know that this is you can set it up to always run this init sequence before the run. But this is the default like initialize hardware sequence. There's another option for each individual test to have its own sort of initialization. This is just a general initialization to get the stack set up. Okay, so let's remove that. Okay, we'll just cancel this. Okay, so what I just did, I did the initialization, it performed a download, it ran until main. So now when we execute this test, it should have no problem. Okay, so the test is running, it executed, it passed. So we did get 0% object code for the function stub. The test function, the function under test, did have 100%, which is what we expected. So that's good. There were 62 actual bytes of code in just 6 lines of code that were executed. So that's basically how the coverage works. If you had a more, sophisticated function that had maybe some branches and stuff, then you could set up some condition coverage here. And so the way the condition coverage is, if you expect a conditional statement to basically you don't care which way it was taken, then you can use this option here, and just percentage of any percentage of certain paths would satisfy the condition any. For condition true only, this is if you expect a certain amount of your branches to be taken only true. That means they don't actually get evaluated as false. Then there's false only, and then there's both. So both is if you expect actually both pathways to be taken, not just one or the other. Both have to be taken in order for the condition both to pass. Okay, so for coverage, so the way this is working for this, I do have the trace. It's recording a trace. We can actually even look in. So I did record a trace. We can actually look in winIDEA at the trace file here. Let's see, trace file. It should be set up. Okay, let's run that one more time. Let's go ahead and run this one. Okay, good. So we've got our iTrace iTest profiler TRD and our iTest coverage TRD file. So this is the timing information and this is the coverage information that we recorded. So basically it's just setting up a coverage within winIDEA and then gathering that information and displaying it in testIDEA. So again, winIDEA is sort of the underlying tool that's being taken advantage of. That's what makes this test tool so unique. It's basically there's a debugger in the background doing all the magic for you. Utilizing the trace, creating the call stack frames, pushing things onto the stack for you, all of that stuff. Okay, but you do have access to the raw files here, so we could save this off for future audit or whatever you'd have, and this information can be saved off and brought back into winIDEA to be viewed in this format as well. Okay, so that's basically how the coverage works. So the other way, so again, this was taken with the actual trace mechanism. The other way to set it up is using a feature called slow run. So if you don't have access to any trace interface, you can use a slow run feature. It does run the code very slow. So what it does is it single steps through the code and collects data similar to what a trace would collect between each step. So, and we can step at about, 50, depending on the clocks and stuff, you can execute about 50 to 100 instructions per second. So, these microcontrollers are used to running in the megahertz, and you'd be running at like, 100 hertz at the most or something. So if you do run in the slow run mode, it takes very, very long to execute, just basic tests. So that's the huge trade-off. But sometimes you just don't have a capability to use a hardware trace, and you can just let this run overnight. So if using the slow run is definitely a viable option. Okay, so that's for gathering coverage. Obviously, slow run won't work for gathering any type of timing information because you're single stepping. That works fine for unit testing. You won't be able to get any real-time profiler information from the slow run feature. Okay, so profiler is where you do get the timing information. Here we have, so we can actually set up timing constraints for lots of different measurements here. Net time, gross time, call time. So this is for multiple instances, nested calls, interrupts, if interrupts are being executed. In a unit test situation, you wouldn't have interrupts, but you could still, measure net time or gross time if you had nested calls enabled. But you're just given this information if you're curious how long it takes to execute your code, in a unit test situation. So you can do that if you have access to both program trace and data trace. You can record, the amount of time it took to execute code or the amount of time it took to change variable values. So this is how frequent was this variable access. So it was actually only accessed 4 times. The minimum time was 364 nanoseconds. The max was 420, and the average was 397. So the other features that are available here are the raw trace data. So this is just a recording of program or data trace. If you want to see kind of a record of what the code actually did during the test, you could use that. Again, this does require the trace, or the slow run would actually work here since it's not recording any timing information. Only the profiler records the timing information. Hill is where we'd set up any outputs for the analog digital I/O module. So digital outputs or analog outputs for testing purposes. Monitor any inputs as well of the system. If you're expecting, maybe a test is expecting a certain input, you can also specify that here as well. We have scripts. So scripts can initialize or de-initialize the target system or just the script, the function that you're going to be executing. So if you need any kind of special initialization, for example, we had a customer that was running some kind of EEPROM failure tests, and they were using this functionality to download kind of EEPROM error data and then running the test with that different error data loaded to the EEPROMs. So with the Python scripting, you can access all the functionality of the debugger. The scripts allow you to basically access everything that you can do in the tool manually. Options is where if you needed to change any options in winIDEA, you could do that. The dry run feature, basically it's called a dry run, where you're just executing all the tests, but you're not checking any of the results. You're just collecting all the results sort of as a starting point to help you write your tests. And then finally, there's diagrams where we can generate call graphs or other types of charts. So some of these do require timing information. So like the sequence diagram does require the profiler to be saved, the profiler information to be saved. So you do have to have access to the trace at that point. Same with the call graph, I believe. So we'll see if we can generate one of these. So here we have the call graph that we generated. We can see after winIDEA runs the unit test, then the data collected is then presented in the call graph. And so you can use that in your reports. So let's take a look at the test report here. We're going to set up the test report. So we configure the styles of report. We got the HTML. We've got our, we're going to open up the default browser. We've got our test environment variables. Okay, this all looks good. Click OK. And so here's the test report. We can see the results, how many tests we had, how many failures, the types of failures. Shows we can go to the coverage report. We can go to the HTML document, to drill down all the way down to the code to see which lines of code were executed or not. And which branch has been taken, which one has not been taken. And all of this can be exported. And so this part of the report shows group statistics. We can see which functions has passed, which functions has not. So it's quite a lot of information that we provide here in this report. We can see the test points here, before, after the faults are injected. You've also got expression, sub-expression results. Okay. So now creating the Python script is the last detail that we'll touch on here. So the test specification basically can run through a script or the testIDEA, and winIDEA actually has the ability to generate the Python script to control the test environment outside of testIDEA. And yeah, it runs the exact same tests. It actually calls the same YAML file. So here we go, iTools to generate test script. And then we define the name of the test script. We've got, the right test specification. We need to enable the JUnit format. That's what enables the support for Jenkins. Okay. So now we'll go back to winIDEA, and there we can actually execute the script. And we'll look for the Python script that we just created. We can open up here. And so we can run it from winIDEA under Tools, run script and wait. And it basically executes the exact same YAML file that testIDEA would be executing, but through a Python script. So it shows how you can automate all of the test functionality. You can use the testIDEA GUI to create the test scripts if you'd like, and then generate the test script and kind of modify how the test script executes. You can add functionality to it that way. Maybe include some other tools like dspace can also be controlled, or other kind of hill or IO tools can be controlled with the same Python script. So we can actually see in the background of winIDEA how how all the tests are being done inside of winIDEA. Just how if testIDEA were executing these tests, they would be still done in. And so we have the test report again, and it's basically the same results. Yeah, basically exactly the same results. And yep, so thank you so much for your time today. We now will check out what kind of questions we got. Okay, so questions. I did get a few questions here. I'll quickly go over some of the questions I got. So one of the questions was, do you really need a special micro with traceability for these features to work? And so the answer is no and yes. So the unit testing itself can be done without the trace interface. So the tracing basically allows you to get access to real-time timing information. So you can be recording timing when the system is running the tests. Without that, you can execute basically all the other functionality can be executed without a trace interface. So doing basic unit tests, setting up stubs, fault injection, all of that stuff can be achieved without an ED device. So only when you need to record what's going on, and obviously you don't want to instrument the code. So the whole point here is using the features that are built into these microcontrollers to achieve very powerful test and debug features without having to instrument your code in any way. Okay. So another question we got was, how would this work on a multi-core device where setting a breakpoint on one core could cause a reset? So actually, when you're doing unit tests, for example, so there's a big difference between unit test and system test. In a unit test environment, basically everything else is held in a halt or a reset type of a situation. So other cores would actually not be executing. You would only be concentrating on a single core at a time. And even then, the code would not be executing in a real-time situation. So in the unit test situation, the code is basically run until main or just until the stack is set up. And then at that point, the debugger just calls functions that you want to test, pushes whatever parameters you're interested in passing to the function under test onto the stack, and then executing that function and then returning back to main or jumping back to main. So it's not a real-time situation for unit testing at all. For system testing, that of course is a real-time situation. So you actually have real code that's executing. You're actually not really influencing like input parameters. All of that stuff is being handled by the actual hardware or maybe some add-on modules. So if you have like the analog digital I/O module, it can be stimulating the hardware when you're running system tests. Or the CAN and LIN module can also be injecting CAN or LIN messages while you're running system tests. So the system test would be the more of the real-time situation where then you could have multiple cores, executing at the same time. Then you really need to kind of use like the trace functionality comes in handy. You'll be testing different functionality obviously during a system test than you would be during a unit test. So we'll probably set up a webinar just on system testing. Since we do see some interest in that, but the majority of interest is usually in the unit test integration test side. At least so the majority of our customers are sort of in automotive space. I'd say probably 80% of our customers are automotive related, and the other 20 are probably sprinkled beyond, within industrial or avionics, some defense, medical, so all the other embedded markets. So let's take a look at a couple more questions here. Let's see. Here's one. So with all this fault injection stubs, are we covering what other tools such as LDA provide? Yeah, so LDRA, they can actually run their tests through our tools. But again, those tests are all instrumented type tests. So one big difference is the type of coverage. So all of our coverage is based on the object code. So it's not one-to-one traceable back to source code. So if you have to do your reporting or your coverage on a source level, there's an extra step that's required from our tool, because all of the coverage is actually done on the object code. So having said that, because we don't instrument our code in any way, or instrument our tests, or instrument your code in order to do these tests, we don't do the traditional MCDC testing. So from an avionics point of view, it can be argued that 100% object code coverage is equivalent, or actually even better than an MCDC test, because you can test things that aren't traceable back to source, things like library code or other generated code that might not have source code that you can trace back to. So that's the main difference between like an LDRA tool and the testing that we do uninstrumented, utilizing like a hardware-based trace. So let's do one more question here. So we have a question: in case of complex branch conditions, does the tool provide all combinations to pass the true result of the branch? So that is actually related to the MCDC type of a test. And so I would say that yes, you can achieve that, but not in the same way that MCDC is achieved. It would take some different pathways that would be executed. The purpose of MCDC is showing how different order of parameters or different pathways through the device can actually end up with different results. And so I am not an expert, to be honest, but my understanding is that you can actually achieve the same type of results with object code testing. So I'll probably have to follow up with that question a little bit. I don't feel like I answered it completely. So I'll follow up with that. And there's a number of other questions here that I'll also follow up with after the presentation. So that'll be it for today. I really appreciate everyone's time and attention during this webinar. I hope you found it informative and beneficial for your projects, current projects, or upcoming projects. So we encourage you to get in touch with us if there's interest in pursuing some test capabilities for your project, or even debug capabilities. So we provide debug and test functionality with our tools. So with that, I would like to thank you again for your time, and wish you a happy week this week, and a happy new year as well. So thanks again for everyone's time. Okay, take care.